Okay. Yeah. So, hey everyone. Happy Friday. What is this? April? I've lost track. We're in April. April 5th. And not last week, the week before was the Nvidia GTC conference, and it is by far my favorite conference of the year. Yes, always has been, not just this year. I learn an absolute incredible amount of scientific information, math optimizations, and hardware optimizations, and all the good stuff that sometimes you don't necessarily get from your day-to-day job. And so it's a really good opportunity. It's a bit expensive, so try to make friends with the Nvidia folks and try to get a cheaper ticket if you can, or just expense it to your company if they usually a trick I do is I convince my manager that I'll do this or that I'll go, and then I'll come back and give a recap to the team or to the community, or so that there's a little bit of like knowledge sharing beyond just me going. And this year also spoke with a bunch of customers as well, which was fun because a lot of my customers are at this conference. And so, few highlights here. I think, yeah, maybe Antje mentioned the book. If not, here's a link to our book. Antje and I wrote this and released it a few months ago, and it's selling pretty well. And we're actually seeing a lot more sales kind of going into the later parts of this year, more than we thought. So I think we were definitely the first O'Reilly book to launch with content around generative AI, modern generative AI. We cover all the fundamentals and we splash in a little bit of AWS. So this is not a primarily AWS book, despite the title. We do show you obviously how to use Amazon Bedrock and SageMaker, but the focus here really is the fundamentals. The book is designed to live 3 or more years. This is just an O'Reilly kind of thing. And I think me and Shelby, the other co-author, did a really great job. So I do recommend that. Also, the big splash here is the new Grace Hopper, and this is what they're calling the super chip. And Grace, by the way, I'll get into this in a bit more detail. We're still on the intro slide here, but Grace is their ARM-based CPU that has been linked using NVLink, cross-linked directly to the new Hopper GPU. So this is a combined CPU GPU. I believe there's 72 GPUs and 36 CPUs or something. I have the exact numbers later, but these are reusing the chip-to-chip technology by the NVIDIA folks called NVLink to create the H200, which is a complete system for high performance computing, large language model training, multimodal training. So we'll get into that here in a bit. This conference was absolutely massive. This is the keynote, was at the San Jose Convention Center. The only time I've been to San Jose Convention Center was to see like Beyonce and, hockey games and things like that. So this place is huge. This is actually before it kind of filled up. So, pretty big size place. Today, we're going to cover hardware. We're also going to cover some software. And at the end, we're going to do a live demo. I have a Jetson 64 gig. I call it the baby A100 right here on my desk. It's hooked up to some speakers and some microphones, and it's hooked up to my laptop so I can shell into it directly. And I'm going to run some fun demos here where we're going to do live video detection, and we can ask questions about the video, which is really cool. I've also and I had demoed this a couple days ago to Antje. I have also cloned my voice, and with the Jetson, and I'm going to be speaking to myself, which is kind of freaky. And I've been teasing Antje by calling her and then playing the AI, and she's been laughing about that. Okay, so let's get into hardware here. This is kind of a sketch drawing. I do have a better drawing here of the sort of evolution of the, all of this hardware, but, really 1964, and yeah, sorry, this is blurry. When I blew it up, it got blurry. These were actually screenshots from the keynote. And so it was a little bit hard to get the exact slides, but maybe if you dig hard enough, you can find the slides. But we've seen everything from the IBM S360 back in 1964, which surprisingly I actually used early on in my career. Windows and oh yeah, wow, Pentium and all this stuff. But really, let's get to the good stuff here. We got AlexNet, and then it kind of led to the 2016 DGX1 that actually predated the Transformer. One cool thing they talked about the original 2016 DGX1, how this was signed. The first one went to OpenAI, and it was signed by Elon and signed by Sam Altman and a bunch of people. And I guess Jensen, the CEO of Nvidia, has this in his office, framed or in a box or in a clear glass case or something. He kept talking about that, which is kind of fun. Fast forward, since the Transformer, 5 years later, OpenAI, ChatGPT. This is when your, mother and or father started asking about AI. And then from then we have this explosion of, fine tuning and guardrails and human alignment and, all the good things. Generative AI, a bunch of startups. That's really my focus these days. And then we've got a new industrial revolution is the term. So here's a little bit clearer picture here, all the way from the DGX1. We got the A100 here back in 2020. This really is what most of my customers had been using until 2022, which launched the H100. And DGX Cloud was launched last year. This is actually not accessible to most folks. A couple of my customers have access to it, but I believe this is going to get scaled out. So this is actually the Nvidia's cloud product, which is pretty cool. The ability to get access to their hardware directly. And then March 2024, this was the month and the year of NVIDIA GTC. We have the GB200. This is the Grace and then Blackwell 200. So instead of Hopper, which is the H, Ampere is the A. That's what the Jetson is based on. So I call the Jetson the baby 100, A100. H100 is Hopper, and B is Blackwell, and GB is Grace plus the Blackwell Superchip 200. So I purposely call this out because I was actually a bit confused as to where we are, because they had also launched the H200, which isn't even on this chart here, but the H200 came out as well during GTC, and that's the next evolution of the H100. I'll get into more of these details later. All right, the Grace CPU. So this is ARM-based. Some specs here. Some of these specs may or may not mean much to you. The LPDDR5X. This is 500 gigabytes per second memory bandwidth. The thing I've come to realize over the last few years working on these, larger customers, larger startups, larger enterprises, is it's all about the memory bandwidth, especially for a transformer. So part of the transformer, part of generating, tokens and like images is compute bound, and then part of it is actually memory bandwidth bound. And I'm going to probably do a follow-up, I think, maybe next month, describing, like going into the gory details. This is some of the stuff that we have in the book, but going into the gory details of where the transformer is compute bound and where it's memory bound and time to first token and things like that. I don't have time for that today, but I think that's a really good follow-up. But also note that the LPDDR, this is different than, so this is your sort of classic, DRAM here. This is not the GPU DRAM, which is typically called HBM or high memory bandwidth. But again, this is the CPU, but the key here is that this is relatively high bandwidth here. Okay. And the other thing to note too is the 900 gigabytes per second. That's the chip to chip. So that's how fast this can communicate with the Hopper GPU or the Blackwell GPU. So there is a Grace Hopper GH, and there is a Grace Blackwell. And Blackwell is the newest GPU, the new B200. Okay. So I'm throwing quite a lot of numbers at you here, but just, just try to bear with me here. There's going to be like quite a lot to cover, and I'll certainly post these slides later. So chip to chip. So backing up a sec, let's remove the GPU from the conversation. And they have also created what is called a Grace CPU super chip. And so this is two of these Grace CPUs that are connected to each other that share memory. They share unified memory, and they can talk to each other at 900 gigabytes per second. Okay. And so this is really, really powerful. We'll see the same exact thing when we see a Grace CPU paired with a GPU, either the Hopper or the Blackwell GPU. So at a high level, something that I was actually surprised with was that they are really focusing on CPUs as well as GPUs. So traditionally, so I always go into these GTC conferences thinking about Nvidia as a GPU company, and I come out like being reminded that they are much, much more than that. They're a networking company through their like acquisition of a company. I always say it wrong, but Mellanax, yeah, I believe. And then also now they're really doubling down on these ARM CPUs and making them highly optimized to communicate with these GPUs. So pretty interesting stuff. So at a very high level, ARM-based SIMD vector instruction sets. They've got the LSE extensions for the atomic operations, this compare and swap, the atomic memory instructions here, add. All of this stuff is just these days sort of table stakes for CPU. Note that there is, and I think I cover this right here. Yeah. So compiling for the Grace CPU, if you've ever tried to take something that's been written for like Intel, for the x86, and try to get it to work for a ARM-based CPU, you probably have felt some of this pain. So there's actually an entire Grace performance tuning guide that really walks you through this. This is not for the faint of heart. I'm actually dealing with this right now, trying to convert some stuff to the Grace CPU and there's a whole lot of flags that you have to know about. And I hit a few dead ends here and there on the internet, and then I find a gem. Someone posted something similar to exactly what I'm trying to do. Also keep an eye, like this is really where Docker can like help you out. Someone likely has compiled something and put it inside of a Docker image, and then you can tell Docker that you want to switch to the ARM-based platform, and then pass that flag into your Docker run command, and then things should work. So that's in theory. That's not exactly how it works, but in theory. And just know that things like BLOS, which is the like linear algebra libraries, PBLOS, fast Fourier transform, LAPACK, and some of these packages have been ported over to the Grace CPU on your behalf, and so try to find those if you can and reuse them. All right, let's talk first about the Hopper 200. So this is the next generation of the H100, which is what all of my customers have been switching to recently, because the H100 still has the 80 gig. Now the H200 has 141 gig, and this is kind of a weird number. It's not quite 2x, but 140 is greater than 80, which means less of the PyTorch out of memory and the TensorFlow like out of memory errors. All right. Also, the max GPU to GPU bandwidth. So this is when you have multiple GPUs on a single node, on a single instance, they can communicate at 900 gigabytes. So honestly, between H100 and H200, really you get a bit more performance or a bit better RAM. And but your GPU to GPU bandwidth stays the same at the 900. There is, let's see, and so honestly, if I were you and you have access to the Blackwell, that's really where I would spend time upgrading here. So the H200 does give you more of the GPU RAM, which is really nice, but we do want to explore the new Blackwell, which we will in one sec. So this is the Grace. So now we're going to talk about the Grace CPU plus the H200, the Hopper 200. And this still has the same 900 gigabyte per second, but this also has unified memory now between a CPU and a GPU. So if you've ever done any GPU programming, you've probably spent, 70 to 80% of your time just trying to optimize how the memory gets from the CPU to the GPU and then back. And doing that super, in parallel so that you're not pausing the GPU, waiting for that memory to load. So you're, typically pipelining things or doing the memory load asynchronously in the background while you're doing compute. A whole ton of that becomes much easier now when you commit to the Grace Hopper superchip or the Grace Blackwell superchip with the unified memory. So from a developer standpoint, from a performance standpoint, things get quite a bit easier with this unified memory. Now, let's jump to the Blackwell. This is really, so there's the B100 and there's the B200. And the key here is native FP4 tensor cores. So if you've worked with these large language models or these large multimodal models, they typically can't fit onto a single GPU. And so most people start to explore quantization. They go from the 32-bit down to 16-bit. Okay, that's okay, but can we really get it down to 8-bit or even 4-bit? And so Blackwell now has native FP4 tensor cores, and this is really where you get the performance. And I believe it's about 30 times the performance of the Hopper generation, the H100, H200. Also 30% more RAM, a little bit of a nicer number here, 185. So, from 80, and this is compared to, let's see, 30% more GPU RAM. Where did I get this number? From the one, compared to the H200, which was the 141. But really, this is more than double of the H100. Okay, so I'll change the slide to specify relative to the H200. Also, the other big thing is the 1.8 terabytes. So this is twice the GPU to GPU bandwidth. So this is massive. Like I said, a lot of folks don't really pay too much attention to these bandwidth numbers. They're thinking from a developer standpoint, I want to be able to load a bigger model, and so the GPU RAM is nice. But really, where the performance comes from is when you can get data between these GPUs or from the CPU to the GPU as quickly as possible. So here's a nice image that I found here. Blackwell is 30 times the throughput of the Hopper, so the B generation, versus the H100. And this is really because of the FP4. So we see a lot of performance gain here. And even more so than the B200. The thing here is where we are comparing FP8, which the B's so B200 without the Grace GPU. So this is Grace GPU plus the Blackwell 200 using FP4. It just blows everything else away. Okay. And so here's the GB200. This is combined CPU plus Blackwell. We've got 32 Grace CPUs, 72 Blackwell GPUs. Oops, sorry about that. Interconnected with the 5th generation NVLink. This is the faster, what was the number here? 1.8 terabytes per second. Now, these GPUs actually act as a single GPU because of this unified memory. 30 terabytes of unified memory. So this is when you sort of walk away from the NVIDIA conference thinking, okay, it's not all about a single GPU or one instance with 8 GPUs. This is about these really high performance systems. These are liquid cooled. These are, relatively energy efficient. They can always do better with that, but things get better and better, especially with these FP4 native cores. And really, this is the building block. This GB200 is the building block of the latest generation of the DGX. It's what's called SuperPod. Okay, I'll pause there. Antje, any questions? Should I keep on rolling?
Yeah, I don't see specific questions here. People are excited by this. Yeah, GPU to GPU, 2 times faster. But yeah, folks, if you have questions, there's one. What is the X in GBX200?
When is the, let me see here. I have to,
And I know those
GB.
acronyms, right? It's it's a lot to take in here.
Yeah, there's DGX. Was there an X? There's DGX. I actually don't know what the X stands for in that case. Was there another X? If you type it in, I could try to take a look for it later, but yeah,
Yeah.
I actually don't know what the X is. Usually it's accelerated, right? All right,
All right, let's
let's
go.
jump to software. Now, I'll say, you know, when I go into these conferences, when I think of the NVIDIA software, I think of CUDA. CUDA, I think we can all agree is, you know, really the NVIDIA that's where a lot of optimizations happen. Some of the reason why CUDA is so specialized is because the you know hardware was specialized for you know back in the day graphics, and then you know slowly became scientific computing. Now you know these large models, generative models. There's a whole lot of really like nifty optimizations. These are called GPU kernels or you know CUDA kernels. There's folks that they classically call CUDA ninjas. Those are typically the talks that I would focus on, and I you know did focus on quite a lot of those. Learn more about the unified memory. Learn more you know of these CUDA kernels that are optimized for LLMs. We'll talk about some of those. However, this year there was a particular focus on their sort of enterprise products. There actually were not as many Kubernetes talks as I thought there were. In fact, I had a slide at the end. I eventually took it out where I feel like there are still some gaps in you know how people are using you know what what companies are currently using today, which is in you know my experience like 99% Kubernetes clusters, and where these GPUs live. And so I do have a feeling, I don't know for sure that the DGX Cloud product is based on Kubernetes. I'm not 100% sure, but it just seems very logical. And I know a couple of years ago when I did, you know, like talk with some friends and watch some stuff online, that there was a lot of NVIDIA involvement in the Kubernetes project. You know, there's NVIDIA Docker, right, support, and they're working with companies like CoreWeave to you know help optimize large clusters on Kubernetes that are using GPUs. I still think there's some more work to be done here, and yeah, but and so there's this enterprise stack that I'll show a bit on where you know now there's like these speech APIs, there's these you know 3D APIs, and these are like think of them like cloud APIs that you can call using the NVIDIA cloud or the NVIDIA enterprise product. Okay. So there are GPU operators, there's you know network operators that are NVLink and Nickel NCCL like optimized. They also had quite a lot of focus and have gone through some renaming of their TensorRT product. At one point, this was called Triton. The name Triton has kind of gone away, and it's called TensorRT LLM. I'll talk a bit more about that. In general, I was a bit confused about the like enterprise strategy. Might be my own, you know, because I was popping in and out of a lot of different sessions, but I did try to go to you know their like marketing pages afterward and try to piece everything together. I was a bit confused about the enterprise strategy. I think if I was working with it more on a day-to-day basis, I might fully like understand it, but I will share with you as much as I was able to glean from my research here. So Some of you might have worked with a framework or a product called Megatron, also called Nemo, also Transformer Engine. You know might have heard about. All of this was very, very confusing and quite honestly still a little bit confusing to me, but this was the best slide that I could find. So all of this seems to be emerging as a Nemo, like, yes, under the umbrella of what's called Nemo. And Nemo is like in this slide is called a framework. However, you'll see later on, and you'll start to see that some of their products are being named with Nemo. Now, where does Megatron fit in? So Megatron Core is really a set of libraries that are, and like optimized GPU kernels that are meant to be extended. And there is this reference implementation of Megatron Core that's called Megatron LM. Okay, so I don't necessarily like how they've drawn this here, but I'm just sharing the slide that was shown. But think of Megatron LM as a reference implementation of the Megatron core, and gives you the ability to then build your own framework. Transformer Engine is also uses Megatron core. It's accelerated right now for Hopper, so that's the H100, the H200, and it's accelerated and optimized for the Transformer models, which of course are very popular. And right now, this is FP8 optimized, and I'm sure at some point for Blackwell, they will become FP4 optimized. Okay, so hopefully I didn't cause more confusion here, but just know that Megatron core is really the core, and then all the other things are sort of implementations. Okay. So here we start to see this I guess marketing or branding of their guardrails. So Nemo is now creeping into the enterprise product by Nvidia, and I think I cover some of them here. There's like Nemo guardrails, so these are going to be topical guardrails, safety guardrails, security guardrails, right? And of course, guardrails, we know from these language models, are extremely important. These have been built into the Amazon Bedrock product as well. You can create your own guardrails, things like that. So if you're doing this in NVIDIA land, you would start with something called Nemo guardrails and extend that. Looking at the time, I don't want to get too much into these details, but I will share the slides. I do want to point out, so this was a slide that I grabbed from one of the talks. I think it's important, and this is the follow-up talk that I'll do. So if this doesn't make sense right now, just know that when you're actually generating text from your trained model, from your pre-trained model or your fine-tuned language model, there's actually two phases. There's what's called a pre-fill phase, right? That's the part that's compute bound. And then there's the decoding phase, which is really the memory bound part of it. Okay, so and the pre-fill phase is where we take all of the tokens from this massive prompt that you send us, or batch of prompts. We do all of the attention calculations, right, which is like an n squared type of complexity, time complexity. And we have to do a whole ton of calculations. We move a relatively small set of data to the GPU. But then it's very heavy on the computation side. On the decoding side, we are generating a single token and and on the pre-fill phase time, the metrics that you want to pay attention to, the main metric is time to first token. So once the pre-fill phase is done, we are going to send back the first generated, what's called the output token, the very first one, back to the user, or we've generated one token. That's the output of the pre-fill phase. From that point on, we will continue to generate or decode more and more. And then you want to start paying attention to a second metric, which is called time per output token, or teapot. And you know, this is really the number of tokens generated after the first, or the time that it took to generate the entire completion, you know, the entire response, and then divided by the number of tokens that were generated. This actually is multiple of these iterations. There's a lot of like memory movement here, and this is why this phase is memory bandwidth bound. Okay, so not a lot of folks really think about that. I've come to realize, yeah, obviously some of the more sophisticated customers that I have certainly do pay attention to these, but this is really where your memory bandwidth is absolutely critical to the speed of the decoding. We will also talk about some techniques to improve the decoding phase here in a bit as well too. Also on the prefill phase, the more data that you can put in, so the larger batches that you can fit into your GPU, the better. This is why the memory is critical. The GPU RAM is critical. So the more memory that you have, the larger batches you can pass in for the same model. Okay, decoding. Yeah, so decoding is memory bandwidth bound. Usually the GPU is being underutilized during the decoding. This is where you start to see dips in your GPU utilization, or your what's called the MFUs, model flop utilization. And so there are some tricks to speed up the decoding, or to do what's called speculative decoding, which we'll talk about in a sec. Also note, you know, the attention mechanism. Yeah, like I said, this is partially, it is, you know, used during both the prefill, where the attention is being calculated and squared all tokens to all other tokens in your input. And then also, and that's populating a key value cache, and then that cache is then used during the decoding. So prefill and decoding phase actually have different characteristics. One is typically, you know, matrix multiply gems, and then matrix vector multiply gem Vs for the decoding. That's assuming batch size 1. But you know, basically, it's not just one operation going through the transformer. There are 2 separate phases. So, and then also this all gets more and more challenging with the unpredictable prompt input length. So sometimes we have a short prompt, sometimes we have a massive large prompt, and this can cause memory fragmentations in your KV cache that's populated during the prefill. So all of these I'm sort of leading up. So these are the challenges of your generative model. And here's some of the ways to combat and to like optimize. So you could do what's called page KV caching. This is like, if you think of, you know, computer like operating systems that do, you know, paged memory, it's sort of that same thing. This helps to remove some of the fragmentation. There's also, of course, tensor parallelism and pipeline parallelism, where you're spreading these you know, matrix multiplies and these operations across multiple GPUs in parallel, and then reducing and then joining the results later. You have something called fused kernels, and you know, things like flash attention that are very aware of the specific GPU that you're using, and can take at full advantage of the L1 caches and what's called the SRAM cache on the GPU. These are even higher bandwidth caches. You know, on your CPU, for example, these would be like the very, very small but close L1 caches. Okay, and then fusing kernels together really takes you know, lots of multiplies and packs them into one kernel, so that you just move the memory once to the GPU and do a whole bunch of operations and then split it out when you're done. So fused kernels is an instant speed up. Flash attention is used by, you know, 100% of the folks that I work with. These are things, you know, these days that you should certainly turn on right from the start. They're basically just turbo buttons. Of course, quantization, trying to get things down to FP8 and now FP4, gives you an instant, you know, memory savings, and you could do more with less hardware. GQA, grouped query attention. This is a technique that really should almost always be used. It's a way to reduce the size of your KV cache. So when you are doing the attention prefill phase, you are calculating, the many to many operation of how each of these input tokens attends to the other tokens in that input. And this can take up a lot of GPU memory, and that's what you're trying to reduce, and you can use GQA for that. On the decoding side, there's something called speculative decoding. So as we all probably know by now, when we are generating, we are actually generating a single token at a time, and we're getting the highest probability token that comes next based on all of the tokens that have been seen. We're doing that one after another in a serial manner. Speculative decoding, actually, so if you're familiar, back in the Spark days, there was something called speculative execution, where you would perform something that's high, that has a high probability that it might actually be the right way to do things. And speculative has been around computer architectures and compilers, and the way instructions are run run at the CPU, GPU level, whatever, where we are speculating what might be the next token, or the next token, and then we are validating it. So think of it, and there's a very common technique called the Medusa speculative decoding. There's a whole paper on it. This has been implemented. I think this might be in SageMaker by now. Not 100% sure, but speculative decoding, so think of Medusa has multiple heads, and what's happening is I can actually generate not just the next token, but the next 8 tokens if I have 8 heads, and then I can sort of then there's a separate model that actually validates. Now, this requires extra memory because there's a separate model that's involved to say, okay, did I actually speculate correctly? If so, I can skip and just, so speculative decoding, we've seen people have really good success. There is a trade-off though of extra model that needs to be trained and learned, and there's also extra memory that's needed, and so extra computations. But yes, overall seems to be working well. There's actually a even newer strategy called speculative streaming. This is a paper out of Apple, of all folks. There is no standard implementation. I believe some of the SageMaker folks have been looking at this, and hopefully they'll be, but speculative streaming gets rid of that extra model and that sort of extra validation stuff, and has a clever way of doing something like this. Okay, and then there's flash decoding, which really helps out with these long context models. So I'll have a follow-up session because I'm going to be diving deep into speculative streaming and some of these other techniques here soon. So group query attention, I'm actually going to skip over this. I think this is pretty well documented, but just know that when you, and specifically for long inputs, long context, long prompts, this really helps reduce the amount of size of your KV cache. Okay, and I had already mentioned the Medusa, so I'm going to skip over this, but just know that we have multiple of these Medusa heads, and I think, is that a llama with the Medusa head? Yeah, that's pretty funny. I didn't notice that before. So you can look into that. There were a few talks, not as many as I thought, on long context window, and I had expected more on this because I think Gemini has like a 1 million token maximum, and of course Anthropic Claude now has 200,000 token limit. We're definitely seeing 30,000, 60,000. I think the new OpenAI is 128,000 or something like that. But really the sort of intuition here is that you need to partition these into smaller chunks and schedule them across multiple forward passes to kind of smooth things out a little bit. I don't have too much information. Again, this is going to be an area that I'll dive into in a follow-up. But just know that this concept of sort of chunking things up and then is fairly common in this world. Okay, FP8. This seems like a bit of a older slide because FP4 is now all the rage. However, FP4 was just launched, and this was a talk that was covering 2023 and some like optimizations that were done for the Hopper, which has FP8 native support. Okay, and let's see, FP8. Oh, and so FP8 has been all the rage because FP8 is like the only 8-bit precision that we had before the FP8 was actually int8. And integers, as you know, don't have anything after the decimal. They're just like integers. And so we would lose, quite a bit of precision by, just using the integers. And so Hopper, the H100, H200 have native FP8 support. Okay. And what that get, and the cool thing about FP8 is that, and do I have a slide on this? Let me look ahead here. Let me just jump ahead to this. So we have FP16 and of course BF16, which is slightly modified. The BF, by the way, stands for brain float. We cover this in the book, but this BF16 came out of like Google Brain. This is a slight tangent. And if you're wondering what the B stands for, it's brain from Google Brain. Yes, FP16 is nice and all, but we see a lot of folks using BF16. And then folks would use int8 if they want to get down to, which I don't even show here because it's kind of boring because there's really no precision. Now, so Hopper introduced native FP8. And the cool thing about FP8 is it's configurable. You could choose to use more precision. You could choose basically how many do you want for the exponent and how many of those 8 bits, or yeah, actually 7 bits because the first one's fixed on the sign. How many of those 7 bits can be allocated to exponent or to mantissa? And this is important because you want to use more precision on the forward pass, and that's what's called E4 M3, exponent for mantissa 3 on the forward pass, but on the backward pass, you want more of the range and less, and you can deal with less on the precision. So this makes things a little bit more challenging because now we need to treat FP8 like differently on the forward pass and on the backward pass during training. Okay, so that was a quick kind of jump ahead there, but yeah, FP8 is obviously better than FP16. Okay, so, and here's a really small thing here, but FP8, so this is the H100 going old school, 2023 style. FP8, those native tensor cores, performing better. This is teraflops here, right? Yeah, so 200 teraflops operating twice the speed of the FP16 tensor cores. So all of these chips have tensor cores for float 32. They all have float 16, FP16, and now as of H100, they have FP8, and as of Blackwell, they have FP4, all right? So real quick, back to FP16, we see some performance gains. I'm gonna skip over this to get to the good stuff here. So, once again, FP8 is configurable, range precision trade-off. Now, when quantizing, we need what's called the scaling factor. And I'm not going to get too much into this, but because we're using 2 slightly different variants of FP8 on the forward and the backward pass, we actually need different scaling factors. We can't use the same scaling factor on the forward pass that we do on the backward pass. So tiny bit more complexity here. How do you choose the scaling factor? Well, it's simple conceptually, but this is actually difficult in practice. Ideally, you would maintain all of the data coming in, and then choose the scaling factor based on what you're seeing. What is actually being used, because yes, everyone's training run will be different. People have different data sets, things like that. So There's a slight optimization here where we are going to use windowing. So we can't keep all of the data and find the maximum across all the data. That's just not efficient. And yeah, the entire high precision output in the high speed memory. So because we are memory bound in these GPUs, it's not sort of infinite. Like we don't have 2 petabytes of RAM like we do in the CPU world. We can use a windowing approach and sort of approximate and then calculate the scaling factor for each of the forward pass and the backward pass. Okay. The other project that I actually didn't know much about until this conference is what's called Transformer Engine, so TE. Now there is FP8 support. That's the hook here. There's floating point 8 support within the Nvidia Transformer Engine. It's a pretty cool project. It has Jack support, PyTorch, and Paddle I believe comes out of Baidu. Supports different types of model parallelism, tensor parallelism. And, so like, keep an eye on this. This is an open source project, implements the FP8, hopefully soon FP4. And I think there was a slide earlier where I showed Transformer Engine. I think it was on the NEMO slide back here. Yeah, so Transformer Engine is built on the Megatron core and had popped up a little bit more than I thought it was going to in this conference. So it gives me a feeling that this is being used more and more. All right, let me do a quick time check here.
Yeah, I just was about to say that, Chris. We have 10 minutes left.
Okay, and I do want to make time for the demo. I'll cover this at a high level. So there's really, so some of the challenges here are we need more GPUs. We have larger models. The sequence length, the context windows are increasing. They're up to 1 million now. How do we deal with all these things? Data parallel only gets us so far. There's something called fully sharded data parallel that comes out of Facebook, or well, was inspired by the Microsoft Zero paper and is now built into PyTorch as of, I believe, PyTorch 2.0, maybe. Tensor parallel, really helps us as our model size grows. We can spread this out across, 8 GPUs on a single instance, node in our cluster. And then tensor parallel also helps with these large sequence lengths as well. Okay, here's some of the details here, which I won't get into here, but again, I'll share this. Some of these come out of papers, some of these come out of talks that I saw. One thing to note here is, if you've heard of the Sora model out of OpenAI, this can, generate videos or even, take videos. And what was sort of interesting to me was a video, and which is of course multiple images kind of being strung together, will like result in 1 million tokens very easily, where token are portions of the image, or pixels. Think of them potentially at the pixel level. You have millions of these pixels, which if you think of those like language tokens, we can very quickly get into the millions for these inputs. And so some of the new optimizations coming out soon, or that are coming out, are for these extremely large context windows beyond language, but also into the image and into the video. So the other cool thing is this activation recomputation. This is where instead of storing all of our activations, we can actually selectively choose which activations are actually faster to recompute. So if you recall me saying that the GPU on the forward pass is on the decoding phase is often memory bandwidth bound, and the GPU starts to idle, right? And so what we can do is and because we are memory bound, we could actually choose to store less of these calculated activations, and choose to recompute them to use the idle GPU to make this trade-off of, okay, I have a compute device that's starting to idle and I'm starting to hit my memory limit, and I can't get data in there fast enough anyway. So why don't I actually use that GPU to recompute selective like activations? And so, there's a whole lot of kernel level decisions being made here, and like optimizations. And really, this is all to sort of get around the maximum GPU memory limits that we're seeing. Okay, and of course you can offload between GPU and CPU. This gets better and faster when we have these super chips of the Grace CPU plus your Blackwell or your Hopper GPU. A little bit more on FP8 with Transformer Engine if you want to get to that level. Couple more of these Transformer Engine features that were launched since GTC 2023. So we see things like group query and multiple query, so MQA, GQA, sliding window, and that's for the attention. That's for some of these larger context windows. We see rope, rotary position. This is also used for large contexts. The Falcon architecture drove this parallel transformer, of course, more CPU offloading. So the transformer engine, which uses Megatron core and uses custom CUDA, these like CUDA kernels that the Nvidia folks are spending the thousands of the CUDA ninjas that they have there. They're spending time building all these. So we'll likely see lots more of these as speculative decoding becomes more popular, speculative streaming, and other large contexts. The NVIDIA math libraries are all, continually being optimized for FP8 and FP4. A lot more focus this year. Well, I wouldn't say a lot more, but continued focus on flame graphs and debugging, and the sort of the addressable market here is folks that can really read these CUDA kernels and read these logs. And one thing on these flame graphs always to remember: when you see these large plateaus, you have a potential performance problem. This means that you're spending too much time in this, and what you really want to see are peaks, quick peaks and drops, and not these sort of large. Kernel fusion, already mentioned this. I could take two multiplies, combine them into one single kernel, and that way I can load all of the memory that it is needed for each multiply. I can combine that into one memory load, do both multiplies, and then pull those out instead of loading this partial memory and then this partial memory to do. I can combine it. So yeah, like kernel fusion is like absolutely critical. There's something called the NVIDIA Inference Microservices, NIMS. And this is their, think of this like their inference server. So CUDA is at the core. TensorRT is the runtime. There's something called TensorRT LLM that builds upon TensorRT. So TensorRT is more generic. This can do, multimodal models, all kinds of stuff. TensorRT LLM is built on TensorRT, which is built on CUDA, and TensorRT LLM is specific to LLMs. The other cool thing about NIM, and NIM is based on these here, is that NIM exposes an OpenAI compatible API that lets you plug in your own models or open source models off of Hugging Face, and it contains the conversation API, the messages API, exposed by OpenAI. Okay, so there's an LLM operator. Here's some JAX stuff. JAX is pretty cool. I actually didn't know much about JAX going into this, but I realized it makes highly parallel. It can do multi-GPU code very, very easily. There's quite a lot of details here. Transformer Engine does support JAX and a lot of primitives. The rest of this is really about MPI, so probably a little bit well, actually just this. So there's this technology called SHARP, Scalable Hierarchical Aggregation and Reduction Protocol. The key here is that Nvidia is putting in network computing. So inside the network, so the ability to offload the networking from the actual GPU nodes and actually put this into the network switches, right? And to the network layer. And yes, Amazon does something similar with our, the term is, yeah, Antje, do you remember the term for the network? Anyway,
The
yeah,
mix.
so every like, the EC2 instances have a chip on them now that handles all the networking so that this EC2 instances focus primarily on the compute. I think it starts with an N. Yeah, I can't believe why I can't. I can't remember this. Yeah, anyway, but it's similar to that idea where we want the GPUs and the CPUs on the GPU instances to be focused on compute, and we want to offload the networking into the network layer itself, into a separate layer. So once again, not as much Kubernetes as I had hoped. Even at KubeCon, I feel like there wasn't that much. CoreWeave has a Slurm on Kubernetes operator or framework that they supposedly will be open sourcing early this year. I checked a couple weeks ago, it still wasn't there. Yeah, once again, you see Megatron, you see Nemo framework, so we're starting to see branding around Nemo here. Okay, and the key takeaway here is that we've gotten to a point where bare metal and Kubernetes are actually very similar in performance. The scaling of Kubernetes is approximately similar, linear to the bare metal, which is good to see. It means Kubernetes is soon not to be the bottleneck. Okay, and the Jetson that I'm about to demo is actually this AGX Orin. And it's 275 teraops. It's a 2048 core Ampere, so that's why I call it the mini A100, baby A100. And let's see, these demos all come from this Jetson AI lab. And oops, what happened here? So let me do the demo. We get this back here, and I have to undo my AirPods, otherwise you won't be able to hear it. How do I disconnect these? If I just put them back, they should disconnect. Okay, we'll fix the audio. Okay, Antje, can you hear me still?
Yes, we can hear you. And I think folks, yeah, I think Chris, what you mentioned before were the Nitro cards on EC2, right?
Nitro, that's what it was. Yep, I was confusing Nitro and Nemo.
Yeah, I was just about to say Nemo too. Yeah, it's the Nitro.
Yeah. Okay, and let me put this in the chat. This is where all these cool things are here. All right, so put this over there. Oh, yeah, looks like you already did. Thanks, Antje. Okay, I'm going to, so I have this running. It's called Llama Speak. I'm using just a standard Llama model. I'm going to turn on my microphone and start talking to this thing. Now, I've trained this with my own voice. And I'm curious if you folks think it sounds like me or if it doesn't sound like me. Hi there, what is your name? Uh-oh. Let me hit refresh here. Clear that. Hi there, what is your name?
Hello. My name is Lars. I'm
Okay, that's actually the stock name. Let me switch it to me.
course. Smiling. Fishy.
Okay.
Great. Your ring is there. Behind something you.
Yeah, so it's not using my name. One sec here. Or sorry, my voice. I apologize, but I'm a large language model. I cannot provide you with a way to hack someone's account or. Yeah, Antje, what'd you think? Does that sound like me?
I think it's kind of scary, but yeah, it's getting there.
It's slower than it was when I demoed it the other day. I don't know why, but okay. So let me kill this demo. And so that's me speaking to it and speaking back in my own voice. I didn't realize I sound like that. Antje, why didn't you tell me I sound drunk or stoned or whatever? Okay. Let me start this demo. This is going to be the video demo. Okay. And real quick, once this loads, it's going to use the camera. So I do have a camera here plugged into the Jetson directly, and it's going to use that. We're using a lava model. Let me see if I can find, where do I specify the model? And okay. And let me click refresh here. This will start streaming the video. Give it a minute. All right. So let me put that in the background. You'll also see kind of cool demo here where it's doing a RAG based on, let's see if I get this going, play. Okay, so it's actually looking up people that in some vector space somewhere inside of a small little vector database that this demo uses called NanoDB. And my favorite is this like shirtless guy down here that's laying on his bed, thinks I'm 66% like that person. There's some pre-canned things here, like describe the image. Let's see, man in a white shirt, that's actually not right. And then what sign am I making? I could do peace sign. I was trying to do like a dog, like rough, or yeah, it does thumb sign, thumbs up. How many fingers am I holding up? So we'll do 5, although it's 4 fingers and a thumb. Ha, 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 ha. And then if I had oh, actually, let's see if it recognizes my hat. Yeah, it does. Yeah, DeWalt. So it can actually recognize that. And I can capture an image here and tag it. And I'll say, this is Chris. My name is Chris. Add it to here. Now I'm showing up. So I am 98% of myself in this vector DB. And there is a way, I couldn't quite figure out how to get it to work, but there's a way to mark when something happens. Like the example that was given that I've seen before is you can ask it like, is something on fire? And it'll detect if you have a flame, like a lighter, it'll say there is fire in the image. And so you could think, this could be used to detect fire, fire safety, fire thing, in, wildfires, things like that. So that's my demo. We're about 10 minutes over. Ansha, are you still here or did you have to drop?
I'm still here. Perfect.
Okay. So that's it. We'll post this. Oh yeah, any questions?
There was a question from earlier. Do you mean N/DPU network data processing units that offload from CPU GPU?
Yeah, exactly. And so Nitro is a form of that. Yep. That's exactly
And
right.
thanks to the folks, who looked up the Nitro. We had a question earlier that's general. Curious if Web3 DPIN tokenization was mentioned at all at the conference.
It actually sounds familiar. I don't know if I just saw it in a talk description or something, but I didn't have any slides on that one. But
Okay.
I'll share this on LinkedIn. Here's my linkedin.com/Fregly. And thanks everyone for coming. Happy Friday. Have a great weekend.
Thanks, everyone. Bye-bye.
Bye.